Do users benefit from interpretable vision? A user study, baseline, and dataset. Many methods for explaining the decisions of deep neural networks exist, but are they actually useful for users? A possible proxy for usefulness is whether users can identify relevant features using them, and we propose a user study design, where we measure participants' understanding of feature relevance using the task of bias detection. To verify whether users correctly found relevant attributes, we need ground truth information about feature importance of a model, and we solve this by creating a synthetic dataset generator consisting of two abstract animal classes called Peaky and Stretchy. The two animals are made of 8 blocks, 4 for the spine, 4 for the legs. Peaky has its head sticking out compared to the legs position, and Stretchy has its head retracted and its legs stretched out. The simplicity of the two animals allows participants to become experts on the dataset within a few minutes of training, and with our generator, we have full control over different attributes: the color of Peaky and Stretchy, their block shape, which can be rounded or rectangular, their background color, and their body posture, including rotation and bending. With our framework, we generated a dataset where the animal color and the block shape attributes were biased, and then use it to train a neural network. But a biased dataset does not guarantee a biased model. To verify that the network actually uses these biases, we varied each attribute in isolation, for example here the background, and then evaluated how the model prediction changed. This way, we were able to measure to what extent the model uses each feature, including the biased ones, for its prediction.
Having a biased model does not guarantee that its biases are difficult to spot. So we needed to conduct a first study to validate this, for which we created a simple baseline explanation technique. An alternative to any sophisticated technique is to inspect the model's predictions on different inputs. We implemented this by showing participants examples where the model predicted Peaky with high certainty, medium certainty, examples where the model was unsure, and examples of Stretchy with medium certainty and high certainty. The image grid we used in this study had 10 rows of such examples. For our study, participants were recruited on the Prolific platform using strict selection criteria. They were shown a video about Peaky and Stretchy and had to complete a multiple choice test assessing their understanding. If failed twice, they were excluded from the study. Similarly, they were shown videos and multiple choice tests about machine learning and biases and their assigned explanation technique. In the main part of the study, they then used this technique to assess the relevance of each of the 5 possible attributes as either relevant or irrelevant, and wrote a short, full-sentence justification for their answer. We conducted our first study with 50 participants. The accuracy in correctly identifying the relevance of the color bias was similar to random guessing, and significantly lower in comparison to that of the model's main feature, the leg position of the animal. The shape bias was not significantly harder to detect than the model's main feature. This confirms that the model contained at least one bias that was difficult to find using the baseline explanation technique, giving other explanation methods an opportunity to improve over these results.
In a second study, we compared the baseline against 2 other explanation techniques. One method used counterfactual explanations from an invertible neural network. Here you can see an image and its representation in the classifier space of the network. We created counterfactual explanations by adding the weight vector to this representation, thereby only changing features relevant to the classifier. The changed representations are then mapped back to the input. For the study, we arranged the interpolations similar to the grid of the baseline method. As a second evaluated method, we used automatically discovered concepts. We extracted the concepts from an intermediate feature map using a clustering algorithm. We visualized the concept by picking 5 images containing it and highlighting the most concept-activating areas. In the study, we presented 10 concepts without showing certainty information. We conducted the study with 240 participants. As an accuracy measure, we used the number of attributes classified correctly. To our surprise, there was no significant difference between the baseline and the invertible neural network. Participants using concepts got less than 2 attributes correct, a result even worse than chance. Our paper also contains a qualitative analysis of the participants' justifications, and we investigate why counterfactuals did not outperform the baseline. Our results emphasize the importance of evaluating explanation techniques in user studies. For future studies, we contribute the 2-for-2 dataset, a study design, and a surprisingly powerful baseline. Finally, We emphasize that any explanation technique should be evaluated against a reasonable baseline.